QoS, what is it and why is it needed? QoS, or quality of service, allows us to prioritize certain types of traffic over others. Different types of traffic place different demands on the network. Video traffic and voice traffic require greater resources from the network. They require more bandwidth to achieve the type of quality that is needed in a phone call or streaming video. Financial transactions are time sensitive and they have greater needs than, let's say, a web page or regular data traffic like sending an email. In this diagram, we're given a general concept of how it works. Packets are buffered at the router, and 3 priority queues have been established: a high priority queue, a medium priority queue, and a low priority queue. Voice over IP traffic in the high priority queue is given a higher priority, so more of those packets are allowed to be forwarded across the network. Financial transactions, which are time sensitive are also given a greater priority, so more of those are allowed as well. And then lastly, any leftover bandwidth is used for the static web page in the low priority queue. When do we need QoS? We need QoS at points in the network where congestion is experienced. This could be points where you have an aggregation of many links, let's say many computers or many users, all having to go up a single uplink or across a single wire. Also, you can have situations where there's a speed mismatch. You're going from a faster link to a slower link. And also, as you cross from a LAN to a WAN, or from the WAN to the LAN, going from network to network across a gateway router. Without QoS, packets are processed as they come in, and when we have network congestion or variations in delay which cause jitter, we experience packet loss. Now, if you're trying to stream a voice call or audio stream and you're experiencing excessive jitter or variations, the playout delay buffer can't tolerate it and packets are dropped due to that excessive jitter. Now, too many packets being dropped results in your call dropping out. Now, with QoS, more voice packets are processed or forwarded because they're in the high priority queue and it's been configured for 0 packet loss. So you still have, let's say, variations in delay and you can have jitter, but an audio stream is able to make up for that, and a playout delay buffer can send out a constant stream of audio information, resulting in a call that experiences 0 drop-off. Voice traffic and video traffic place a greater demand on the network and are 2 of the main reasons for QoS. There are some differences, though, between voice and video. Though they are both demanding, voice packets do not consume a lot of resources because they're not very large and they're fairly steady. So the characteristics are smooth and benign in regards to the demand it places on the network. However, voice traffic is sensitive to drops and delays and therefore requires prioritization. Packet loss should be no more than 1% with voice traffic, and voice traffic requires at least 30 kilobits per second of bandwidth. Now, video traffic is more demanding. The size of the packets that it sends across the network are more bursty and more greedy. It consumes a lot more resources. It's also sensitive to drops and sensitive to delay, and it requires no more than 0.1 to 1% loss of packets and requires at least 384 kilobits per second in bandwidth. In this next graphic, you can see some of the differences. you can see that the audio samples of voice packets are fairly consistent at 20 milliseconds per sample, and the size of the packets are very small. However, video packets, depending on the frame of video, if there's nothing changing in a frame, then they might not have a lot of size. But if there's a lot of action, let's say, in the video or in the movie, then the frames are going to be very greedy or very large. So you can see that it places a greater demand on the network. Data traffic is different from voice and video traffic in that it's generally not as demanding. Also, a lot of data traffic is sent with TCP applications, which can retransmit and are therefore insensitive to drops and delays. There are different types of data traffic. There is mission-critical data traffic and non-mission-critical data traffic, interactive traffic and non-interactive traffic. If you have interactive mission-critical traffic, like in bank transactions or purchases, then there is the expectation of a quick response time in the data. However, a lot of traffic is not interactive and not mission critical, let's say a standard web page, and can therefore be the least prioritized. If we look at the queuing strategies for QoS, FIFO queuing, or first in, first out queuing, is basically the absence of QoS. In other words, packets that enter the router leave the router in the same order. Compare this with QoS and weighted fair queuing, or WFQ, and packets that come into a router, let's say, are then classified and prioritized based on the classification. So high classification packets are prioritized when they're sent out of the router. A newer form of weighted fair queuing is class-based weighted fair queuing, where specific classes of traffic can be configured by the administrator and used to prioritize different types of traffic. In order to guarantee that voice traffic is prioritized to the point where there's no drop-offs, low latency queuing can be used with class-based weighted fair queuing to prioritize voice packets above all else, ensuring that voice calls will not drop off. The example you see here is a combination of low latency queuing, a priority queue, in combination with class-based weighted fair queuing to achieve that very result. In a very general understanding of QoS mechanisms, let's first look at the QoS models. The best effort model is not really an implementation of QoS, as packets are delivered on a best effort basis, and QoS is not really required or configured. The integrated services model, or IntServ model, provides a very high degree of QoS to IP packets with guaranteed delivery. It uses a signaling process known as RSVP, or Resource Reservation Protocol. The IntServ model can severely limit the scalability of a network, and it is demanding on resources and therefore doesn't scale well for large or enterprise networks. The differentiated services model, or DiffServ model, is a highly scalable and flexible implementation of QoS. It works off of manually configured traffic classes, which need to be configured on routers throughout the network. If we look at some of the benefits and drawbacks of the best effort model, you can see that under benefits, no special QoS mechanisms are required, and it is the easiest and quickest model to deploy. However, under drawbacks, notice that there are no guarantees of packet delivery. No packets have preferential treatment, and critical data is treated the same as casual email is treated. Basically, this is a non-QoS solution. Now compare this to the integrated services model, looking at some of the benefits and drawbacks. Under benefits, you can see that the int-serve model has tighter QoS for real-time traffic, uses the signaling protocol RSVP, Resource Reservation Protocol. It requires end-to-end signaling and per-request admission control. It uses packet classification, policing, queuing, and scheduling. Under drawbacks, notice that the int-serve flow-based approach is not scalable to large implementations such as the internet, and the integrated services model is rarely deployed by itself alone. Looking at this diagram, we can see that end-to-end signaling is required in the integrated services model. RSVP is implemented on the routers within the network and can be implemented on the hosts as well. Notice the QoS-aware nodes. Sessions and resources are dynamically reserved, one flow at a time. Now, looking at the differentiated services model, we can see some of the benefits and drawbacks. Under benefits, the differentiated services model provides better QoS scalability. It is a defined class-based approach, defining the policy and priority at the routers, known as per-hop behavior, or PHB. It uses packet marking directly in the packets. In other words, packets are marked at the routers. It can also use the NBAR or NBAR2 network-based application recognition services. It uses the 6-bit differentiated services code point, or DSCP, in the IP header, and is also used with IPv6. Under drawbacks, it doesn't provide the absolute guarantee of service that integrated services does, and it requires a set of complex mechanisms to work throughout the network. This is why differentiated services is often used with integrated services. Both the integrated services and the differentiated services models are not exclusive, and they can be used together. In this diagram of a differentiated services example, you can see that the QoS nodes are unaware that QoS is being implemented across the network. That's because a manual QoS policy has been configured on the routers in the network. Notice that as traffic goes across the network, the traffic is classified and colored. We can categorize QoS implementation tools into 3 broad categories: classification and marking tools, congestion avoidance tools, and congestion management tools. Under classification and marking tools, session traffic is classified into different priority groupings, and packets are marked. Under congestion avoidance tools, traffic classes are allotted network resources. Some traffic may be selectively dropped, delayed, or remarked to avoid congestion. Weighted random early detection regulates TCP data traffic in a bandwidth-efficient manner before tail drops caused by queue overflows, basically congestion, occurs. And under congestion management tools, when traffic exceeds available network resources, or we have congestion, then traffic is queued to await the availability of those resources. Common Cisco iOS-based congestion management tools include class-based weighted fair queuing and low latency queuing, or the CBWFQ and LLQ algorithms. If we look at this diagram, you can see the three sets of tools being used in sequence, from the ingress interface on a router to the egress or exit interface of the router. You can see that traffic is first classified and then marked. Notice in the graphic how the packets before being classified are all seen here as gray. As they're classified into different classes, they're marked in the IP header, indicated here with the colorization of the different packets. Congestion avoidance is where traffic is policed and selectively dropped. This is where network resources are allotted into different priorities. Packets are put into different queues based on different weights or sizes. The main congestion avoidance tool that's used in Cisco devices is weighted random early detection, or WRED. If queue buffers fill up, packets may be dropped proactively as to avoid congestion. Lastly, we have the congestion management section where packets are put into their queues and are scheduled and shaped based on the network priorities or policies that have been applied. If we look a little closer at QoS traffic marking, we can see that traffic marking happens at both Layer 2 and Layer 3. At Layer 2, we have Class of Service, or CoS, which happens using the 802.1q VLAN tagging and 802.1p quality of service protocols. Traffic marking at Layer 2 happens on the local area network and is limited to the LAN using Layer 2 switches. Under Wi-Fi, traffic marking happens with the Wi-Fi Traffic Identifier field, or TID. With MPLS, you have the Experimental, or EXP field, also at Layer 2. At Layer 3, with IPv4 and IPv6, we use the TOS and traffic class fields using IP precedence, or IPP, and DSCP, the Differentiated Services Code Point. With Layer 3 traffic marking, the marking can go from router to router, and therefore the QoS marking can be carried end-to-end across the network. In this slide, you can see how QoS marking happens at Layer 2. We have an Ethernet frame, and the 802.1q protocol can be inserted between the source address and the type length field. You can see the two fields inserted into the Ethernet frame, the TPID field and the TCI field, or Tag Control Information field, which contains a 3-bit PRI priority field which identifies the class of service, or CoS marking. The class of service markings have 6 different values: best effort, medium priority data, high priority data, call signaling, video conferencing, and voice bearer for voice traffic. Bits 6 and 7 are reserved for network control information. At Layer 3, QoS is implemented in the IPv4 and IPv6 packet headers in the type of service field and the traffic class field. In the older implementation, class of service at Layer 3 was implemented using IPP and TOS. The IP precedence is 3 bits, and the type of service is 5 bits, and you can see them there in the 8 bits. The classifications have 8 levels, which map to the Layer 2 class of service. You can see there routine, priority, immediate flash, flash override, and critical. Once again, values 6 and 7 are reserved for network control information. The current implementation of QoS uses the Differentiated Services Code Point and Explicit Congestion Notification fields, or DSCP and ECN. DSCP and ECHN map directly over the 8 bits of the IPP and TOS fields, and the DSCP field is backwards compatible with the IPP field. You can see in this example that an IPP classification of 5 involves the 1 here and the 1 here. If you have IPP and you have 3 bits, then this would be a 4 and a 1, which would be a 5, which would signal a critical flow. Under the DSCP specification, you have 6 bits, 1, 2, 3, 4, 5, 6, and this is a 32, and this is an 8, and 32 plus 8 is 40, so you can see how it would map a 5 under IPP using 3 bits, or a 40 using DSCP using 6 bits. Since DSCP uses 6 bits, there are 64 possible classifications of traffic. QoS marking happens at trust boundaries, and marking should happen as close to the source as possible. Endpoints like voice over IP phones, wireless access points, and video conferencing gateways have the ability to mark QoS packets, as indicated in number 1. Traffic can also be marked using layer 2 switches, as in number 2, or at layer 3 using layer 3 switches and routers. As packets travel across the network, the remarking of the traffic can be necessary. The remarking of class of service values, or IP precedent values, or DSCP values. The main mechanism of congestion avoidance in QoS on Cisco routers and switches is weighted random early detection, or WRED. With weighted random early detection, a percentage of the packets are dropped once we've gone over in a queue the minimum threshold. If the queue has gone over the maximum threshold, then packets are automatically dropped. In this image, you can see the difference between traffic policing and traffic shaping. In traffic policing, when the traffic rate reaches the configured maximum rate, excess traffic is dropped. The result is an output rate that appears as a sawtooth with crests and troughs, as shown in the graph at the top. With traffic shaping, excess packets are retained in a queue and then rescheduled for later transmission over increments of time. The result of traffic shaping is a smoothed packet output rate as shown in the bottom graph.